In this video, we're going to talk about something called the scalar triple product, which is defined for three vectors in three space. We do need to be in three space because the cross product is going to be part of the definition. So if I have A, B, and C, three vectors in three space, the scalar triple product is defined as the dot product of A with the cross product of B and C. So B cross C will give me a vector in three space, which I can then dot with A. That gives me the scalar triple product. Now I put up here an equivalent definition. I could also form this 3 by 3 matrix where I put in A, B, and C as the three rows and just calculate the determinant of that. Now let's take a look at why these are equivalent definitions. All right, if I were to take a look at the cross product, B cross C, that would be a symbolic determinant where the first row I would have I, J, and K instead of the components of A. But the second and third rows of this symbolic matrix would just be the vectors B and C. So they'd be exactly the same as the second and third rows of the matrix that I have right here. Now, if I calculate this cross product, I'm going to get some I's, some J's, and some K's. The number of I's I get is the determinant of this 2 by 2 matrix. B2, B3, C2, C3. Of course, I could work that out. I'm just going to write it in determinant form right here. The number of J's I get is the opposite of the determinant of this 2 by 2 matrix. B1, B3, C1, C3. And the number of K's I get is the determinant of this 2 by 2 matrix. B1, B2, C1, C2. So those are the entries of the cross product. Now when I take the dot product of this with A, I'm going to multiply this by the first component of A, which would be A1. Notice, if I calculate this determinant, expanding on the first row, I would multiply A1 by exactly that same 2 by 2 determinant. Now if I'm dotting this vector with A, I would now multiply this by the second component of A. But if I were continuing to expand the determinant on this first row, I would take A2 and I would multiply it by the opposite of this 2 by 2 determinant. Similarly, the third term that I get would be A3 times this 2 by 2 determinant, which is exactly the third term in the dot product of A with this cross product. So I can think of the scalar triple product either of these two ways. Now, I mentioned this back when we first introduced determinants, that this scalar triple product is going to have a really nice significance. If I take these three vectors A, B, and C, and I put them with their tails together, like so. Okay. So let's say maybe this blue vector is B, this orange vector is C, and I'm going to let this red vector here be my A. Okay. So I've got that. They form this nice parallelpiped, is what we call this. Now I'm showing you a model in which we have a non-degenerate parallelepiped. So this would actually determine some volume. Okay. Now, of course, I could have a degenerate parallelepiped if any one of my three vectors were 0, if two of the vectors were parallel, or even if none of them is parallel to each other, if they all lie in the same plane when I put their tails together, I would have what we call a degenerate parallelepiped. It would have no height to it, and so it would have 0 volume. What I want to do is prove, in the case that we get a non-degenerate parallelepiped, that the volume of that is actually just the absolute value of the scalar triple product. Now the scalar triple product could be positive or negative, because I know dot products can be positive or negative, and I know determinants can be positive or negative. Volume is not negative, so we will have to take the absolute value, but I'd like to see if we can't prove that in the non-degenerate case. And then it's going to be true that if we have the degenerate case, the scalar triple product will actually give us 0, and so that will be the volume of the parallelepiped. It will just be the volume of a degenerate one. All right, so let's take a look. I'm going to draw this. So I'm using the blue vector, which we said was B, and the orange vector that I said I was going to call C to determine the parallelogram that's the base of this shape. And then I said, let's call that red vector A, and let's let that be the one that's sort of determining the height of this shape. All right, so let me get this drawn in here. All right, so there's our non-degenerate parallelepiped. And let's see if we can't calculate the volume of this thing. Now, the volume of any shape like this is just going to be the product of two things. It's the area of the base times the height. Now, the base would be this parallelogram here that's determined by B and C. So that's a parallelogram that's determined by two vectors in 3 space. Well, we've learned that that's just the magnitude of the cross product of those two vectors. So the magnitude of the cross product of B and C is going to give me the area of the base. Now, for the height, I can't just say that that's the magnitude of A. It would only be that if A was actually perpendicular to the base, which it could be, but let's not assume that it is. In order to get the height, what I would need to do is drop a perpendicular from the top of the shape down to the base. Now, I don't know what point on the base is going to be directly below here, so it's difficult to just calculate that point and then measure that distance. But I do know a vector that is going to be perpendicular to that base, because anything that's perpendicular to that parallelogram determined by B and C is going to have to be perpendicular to both B and C. So it's mutually perpendicular to B and C. Well, the cross product is going to do that. So I know that B cross C is going to be perpendicular to the base here. Now, I don't know whether it's pointing up or down. I'm just going to be a pessimist. I'm going to suppose that B cross C actually points in the wrong direction, that it sort of points down. But I know that it's making a right angle with that base. Now, it determines a line here that would also therefore be perpendicular to that base. And I know that if I take A and I project onto B cross C, I'm really just projecting onto that line. Now notice, I said what we want to do is drop a perpendicular down to the base here. What I'm choosing to do instead is actually drop a perpendicular sideways onto the line determined by B cross C. But if I do that, this vector right here, I'm going to just call it H because its magnitude is going to be the height that I'm looking for. That's going to be the projection of A onto B cross C. And the magnitude of that vector will be the perpendicular distance from the top of the parallelepiped to the base of the parallelepiped. So I can say the height is just the magnitude of this height vector. Now, I'm going to just focus on that for a moment, and then we'll come back and we'll multiply it by the area of the base. So the magnitude of the height vector is the magnitude of the projection of A onto B cross C. But I can work out what that looks like. So we're calculating the magnitude of, when I project a vector onto B cross C, I'm going to get a multiple of B cross C. And what I get as the scalar coefficient here is going to be the dot product of the vector I'm projecting and the vector I'm projecting it onto. Notice that right there is that scalar triple product, A dotted with B cross C. Now divided by the magnitude of B cross C squared. So we're trying to calculate here the magnitude of this vector, which is a scalar multiple of B cross C. Now we've learned how to take the magnitude of a scalar multiple of a vector. We simply take the absolute value of the scalar multiplied by the magnitude of the vector. So if I do this, now the scalar here is this fraction. The denominator is the magnitude of B cross C squared, so that's already positive. The numerator is this dot product. I don't know whether that's positive or negative, so I'm going to have to put that one in absolute values. And then I multiply that by the magnitude of B cross C. Now, one of these factors of the magnitude will cancel. So I'll end up with the absolute value of A dotted with B cross C over one copy of the magnitude of B cross C. That is our height. So now, let's go ahead and plug that in for our height. So we said the volume was the area of the base, which was the magnitude of B cross C, times the height, which we've now calculated is this fraction, the absolute value of that scalar triple product, A dotted with B cross C, all over the magnitude of B cross C. Now that magnitude of B cross C cancels, and what I'm left with is exactly what I claimed we were going to get for that volume. It's A dotted with B cross C, the absolute value of that. So this proves in the non-degenerate case. We did suppose that we were getting non-zero volume, which means we had a non-zero area of the base and a non-zero height. But this proves that in that case, the volume of that parallel pipette is going to be the absolute value of the scalar triple product, which is kind of cool. This is the three-dimensional version of what we've seen is true if you take the absolute value of the determinant of a 2x2 matrix. That gives you the area of the parallelogram that you get in 2 space. If you take the absolute value of the determinant of a 3x3 matrix you get by putting A, B, and C in as the rows, because that's equivalent to the scalar triple product, you get the volume of the parallel pipette that those 3 vectors determine. So that's kind of nice, and we actually have, I've got to refer to my notes here to see if there's a theorem number for here. There is not a theorem number. Sorry, I thought there was. But there's no theorem number to go with this fact. But it turns out it is true that this scalar triple product, A dotted with B cross C, will equal 0 if and only if A, B, and C are coplanar. Coplanar just means that they can all be drawn in the same plane. If I translate them so that their tails are together, they all lie in the same plane. Now that will be true, of course, if either any one of these vectors is 0, because then I can put the 0 vector as a dot in any plane, and then I've just got 2 other vectors. That would be true if 2 of the vectors are parallel, and it could also be true if I don't have either of those conditions. Here's an example of 3 vectors, none of which are 0, none of which are parallel, but they all lie in the same plane. So any of those circumstances, that will give me that the scalar triple product is equal to 0, so that we can say in all cases, both the non-degenerate case that we proved with this geometric argument, and the degenerate cases where we get 0 volume, the absolute value of the scalar triple product is the volume of the parallel pipette determined by the vectors A, B, and C in 3 space.